So good morning. Today we are going to discuss the lecture number 37. Okay, it comes under synchronous motor. Synchronous motor, principle of operation. Operation. Okay. First introduction. Introduction. The synchronous motor, which is nothing but it is the AC machine, and it will be running at a constant speed. Constant speed. Constant speed means synchronous speed. It will be running. Okay, and based on the load, speed will change. Speed will change. And this synchronous machine, it is available with rating 15 kilowatts to 15 megawatts. Understand? So the speed available here, it is a minimum speed is 150 rpm to 1800 rpm. Okay, so based on the specification, there will be a variation in the speed. And the major definition of this synchronous motor, which converts synchronous motor will converts electrical energy, into mechanical energy. Okay, so the construction parts are available in the synchronous motor are just similar to induction motor. Constructions of synchronous motor similar to induction motor. Induction motor. So here also there will be a rotating magnetic field will be produced. Rotating magnetic field will be produced. You peoples are already familiar about the rotating magnetic field. It is a field or flux. Okay, so which is the field or flux which having a constant amplitude, which having constant amplitude. So whose axis or rotates in a plane at a certain speed. Okay, so based upon the speed, the flux value will be vary, which having a constant magnitude. Okay, which having a constant magnitude. So in this diagram, you see this diagram, This is the three-phase waveform. Okay, three-phase waveform. This first one will be a R phase, second one is Y, third one is B. So the phase value will be sequence will be R, Y, B. The phase difference will be for each phase will be 120. So the total it comes around 360 degree. Okay, the total which is comes around 360 degree. Okay, so here the flux produced in R phase, that is phi, we can write phi 1, or it should be phi r. Phi r equal to, this is the magnitude. Okay, this is the magnitude phi m. Phi m. So phi m into, it is sine waveform, sine omega t, which is equal to this omega t is nothing but theta angle. Phi m sine theta. Phi m sine theta. Okay, this is for phi 1. Okay, R phase. That's what I have written in red color. Okay, R. The second one will be Y. Y phase. Phi 2. Okay, or we can write phi y. Phi y equal to phi m sine omega t minus 120 degree. Omega t 120 degree, we can write phi m sine of, instead of omega t we have to write theta. Theta minus 120 degree. This is for phi r. Okay, this is phi r. This waveform. This is phi r. Are you understand? Phase difference. Phi r. And phi y, it is phi r means this one. This waveform. And the phase difference between R to Y, it is 120 degree. And third one, which is B phase. B phase. This is the B phase. Blue color. Okay. The phase difference between Y to B, which is 120, and B to R, which is also 120. So phi 3, or we can write phi p equal to phi m sine of omega t minus 240 degree. Therefore phi m sine of omega sine of theta minus 240 degree. Okay, so please take down the theta is a angle, theta equal to omega t, where omega is angular rotation, angular frequency, omega equal to 2 pi f. Omega equal to 2 pi f. Theta equal to omega t, where omega equal to 2 pi f. You understand my point? Okay, omega is the angular frequency, theta is the angle, and the sequence which we are maintaining here, it is, the sequence should be R, Y B. Again it should be R Y B. Again it should be R Y B. Okay, this is the sequence of rotating magnetic field. Sequence of rotating magnetic field. I understand. And one more thing, the direction of this rotating magnetic field, which will be applicable in terms of, there will be a reverse direction is also be possible. The reason is that you can take down the direction of rotating magnetic field is always from the axis of leading phase of three-phase winding. Towards lagging phase of the winding of this winding. For example, the phase sequence. Consider the phase sequence. What is the phase sequence? It should be R, Y, B. Phase sequence I am taking R, Y, B. Okay. So this R phase, which leads Y phase by 120. Okay. The phase R leads phase Y by 120 degree, and in similar manner the phase Y leads phase B by 120 degree. Okay, so therefore the rotating magnetic field which rotates from axis R to Y. Okay, therefore the rotating magnetic field rotates from the axis of R to phase R to axis of Y, and then to axis of B. Okay, first it should be go to R to Y, then Y to B. So this type of direction is known as, okay, this direction is known as clockwise direction. This direction is known as clockwise. Direction. Okay, so in synchronous machine, this direction, clockwise direction, we can change. Okay, this direction, that is clockwise direction, can be reversed. By how to reverse this direction? By changing any two terminals of three-phase winding. Any two terminals of three-phase supply. Three-phase supply, or we can say winding. What is a any two phases means? General sequence should be RYB. Okay, if you change the sequence should be YRB. Okay, that's what it is denoting. Okay, YRB. YRB. Okay, now I will explain. I will draw the diagram for clockwise and anti-clockwise direction of rotating magnetic field. Okay, so please listen carefully. Okay, for clockwise, how to draw the winding means, understand, this is R phase, okay, Y, this is B. Okay, now this RYB we have to join. We have to join. It should be connected to the terminals. It should be connected to the terminals. It is connected to Y. Okay, so this line, this terminal will be R, this terminal will be Y, and this terminal will be B. Okay, this terminal will be B, and this is the jumper. Okay, that is, there is no connection. There is no connection with Y. So now you have to mark the label. This is R phase, or this is B, this is Y. Okay, and this is my neutral because it is star connected. Okay, it is star connected. This is neutral. So when you give the supply, okay, this is three-phase supply. Okay, the current flowing in R phase, it is IR. The current flowing in Y phase, it is IY. The current flowing in B phase, it is IP. Okay, IP. So the rotating magnetic field, okay, the rotating magnetic field, that is nothing but RMF. Okay, RMF is nothing but, which will be flux. Rotating magnetic field is nothing but flux. Okay, phi. Okay, so which rotates from R to Y, then Y to B, then it moves to B to R. Okay, then it moves to B to R. So the angle between these two, which is how much angle? It is 120 degree, and Y to B is also 120, and B to R is also be 120. So the total rotation will be 360 degree, that is for one cycle, that is one rotation. Okay, 360 degree rotation. Okay, so this type of movement is known as clockwise. Okay, clockwise direction, clockwise direction, or we can say clockwise rotation also. Okay, the sequence should be R Y B. Okay, any doubts? This is nothing but clockwise. Understand? Okay, clockwise direction, rotating magnetic field which runs in clockwise direction. Okay, in terms of anti-clockwise direction, in terms of anti-clockwise direction, so how to draw for anti-clockwise? Same, take R phase, same take R phase. This is R phase. This is Y. Y. And sorry, in this previous diagram I've done a mistake here. Okay, uh, sorry, and this one should be R phase, because I have put a different, the color will be different. Okay, the color is different, sorry. This is Y. This is B. One second. This is B. Okay, R Y B. Understand? So this is clockwise. In anti-clockwise, same three phase which we are taking, and this three phase will be connected to RYB. Okay, RYB. Okay, so this is nothing but R phase, this is nothing but Y, and this is nothing but B. This is neutral. Now here the phase terminals, how to change the terminals means R phase you can connect it as it is. For Y terminal, okay, this is a terminal which is available in the board. Okay, the Y terminal will be connected to B. For this I mark pink. Y terminal is connected to B and B terminal is connected to Y. Okay, so the sequence will be R B Y. Okay, this is a sequence which we are giving. Okay, now if you change the sequence, the machine will be first moving from R to B, then it moves B to Y, then it moves Y to R. Okay, the angle will be same. It is 120 only, it will be coming. It is 120 degree. Okay, this is 120, this is 120, but the sequence will be different. So here the rotating magnetic field, that is flux, will be produced in anti-clockwise direction. Anti-clockwise direction. Okay, anti-clockwise direction. So when the rotating magnetic field will be produced in anti-clockwise direction, means if you change the terminal, okay, the terminals will be changing it. Okay, next one, next title, it is a construction. 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 There are two construction. There is no difference, much difference between generator and motor. Okay, in terms of a DC machine, and this synchronous motor construction is basically similar to a rotating field type alternator. So there you are seeing there are two major parts are available. One is stator, another one rotor. Okay, there are two major parts are available. One is stator, another one is rotor. You see this diagram. Okay, so this diagram is the construction diagram of synchronous motor. Okay, the synchronous motor construction is just similar to the alternator as well as DC machine. So this big circle, call it as a, which is the protection cover for machine. Okay, protection cover for the machine. Inside there will be a stator. This stator is nothing but, which is the slot. Okay, a small circle you see in that. Okay, this is this type of shape. It is the conductor. Okay, the conductor is nothing but it is a wire. Okay, the conductor is nothing but a wire, and this is the slot duct, we can say. This is the wire. Okay, the combination of these all the conductors is known as stator. The stator is having a three-phase winding, either in star or delta. So we have to give a three-phase supply. Okay, three-phase supply to the stator winding. Okay, to the stator winding. Inside you see here, this is known as rotor. Okay, rotor is nothing but it is a field winding. Rotor is nothing but it is a field winding. This one. And this one, what type of rotor? It will be a salient pole structure. Okay, it will look like some curve will be have taken place in the top layer. Okay, skewed curve will be there. This is known as salient pole rotor. Understand or not? So the difference between the gap between the stator and rotor, there will be a small gap will be there. This is known as air gap. Understand or not? So here the rotor is connected field winding. This winding, okay, this winding you see here. This is the field winding. Okay, so which is connected with a DC excitation. Okay, which is connected with a DC supply, maybe 10 volt or 5 volt we have to give time voltage, DC supply. Okay, so in stator we are giving the AC supply, but in rotor it is a DC supply. This stator is nothing but which is having a armature winding. Armature winding means the windings are connected. That is nothing but armature winding. It will be constant winding. Okay, so in rotor the field winding will be there. Now by giving the DC excitation only, a rotating magnetic field will be produced. Okay, the rotating magnetic field is produced. Okay, a rotating magnetic field is produced. Then there will be a flux will be moved in the rotating magnetic field move in the clockwise direction. Then we can measure the speed in the rotor. Okay, in the rotor. Now the synchronous machine will be constant speed. Okay, so here we are setting synchronous speed ns is equal to 120 fs by p. Okay, it is in rpm, revolution per minute, where fs is the supply frequency. So how much is supply frequency which we are giving? It is 50 hertz, and the p is nothing but number of poles. Number of poles. When the speed, synchronous speed increases, the number of poles will be decreases. Okay, number of poles will be decreases. Principle of working operation here. Okay, synchronous machine which works on the principle of magnetic locking. Principle of magnetic locking. Okay, magnetic locking. Magnetic locking means this is the north pole and this is the south pole. Okay, the flux will be flows towards a straight line between north pole and south pole. This is nothing but tremendous force of attraction. Tremendous force of attraction. Okay, so these two poles, that is these two magnets, okay, north magnet, south magnet, which will be attracted, this concept is known as magnetically locked. Magnetic locking. Magnetically locking. Okay, magnetic locking means when the two unlike poles are brought near each other, if the magnets are very strong, there exists a tremendous force of attraction between these two poles. Okay, in such a conditions, these two magnets are said to be magnetically locked. Okay, again I will explain. Magnetic locking means when the two unlike poles, okay, there will be a north pole and south pole, which will be brought to each other, near to each other. So whatever the charges will be available in this first pole will be attracted by another pole. Okay, so this is nothing but here there will be a tremendous force of attraction. Okay, this concept is known as magnetic locking. Now if these two poles are in rotation, okay, are in rotation, it is in rotation. Okay, if two poles are in rotation, that is if two magnets, or we can say it will be a pole. Okay, if two magnets or poles are in rotation, so rotation means it will be like this. Okay, it will be a rotation. So in the rotation, this is north and this is south. So based upon this rotation, the flux lines, okay, will be attracted in a straight line manner. Okay, so which is also be, okay, it is also be rotating the same direction, as well as the same speed will be flowing. Okay, this concept is also known as magnetic locking. Magnetic locking. That is, the poles are in rotation type also. Whatever the forces will be attracted, which should be in the same direction. Okay, which will be in the same direction. That is known as magnetic locking. Okay, so this principle only we are applying in this motor operation. Okay, motor operation. Or understand my point? Or understand? So when you give the field winding, when you give DC supply to this field winding, it will be produced these two poles are rotating in the same directions. Okay, so these two magnets, that is, if these poles are rotating in same direction, at that time we can measure the speed. Now you want to, because a synchronous machine will be a constant speed, now if you want to change the speed, means we have to change the load. Okay, so if you change the load, okay, if load changes, if you change the load, if load changes, then the speed will be change. Speed will be change. But synchronous machine will be a constant speed. Speed will be change. And understand? As well as the synchronous motor, which is also like alternator, synchronous motor is not a self-starting motor. Take down, synchronous motor not is not self-starting motor, which is not self-starting motor. Okay, you see this diagram. This diagram you see. When the north pole and south pole are in, it is in rotation based upon the axis, we can get this effect is known as magnetic locking effect. Okay, so when it rotates in another direction, okay, which is rotating in another direction also, we can get a torque. Okay, so based upon this rotation, the torque will be produced. The T is nothing but torque. T is nothing but torque. Torque is produced in the rotor side. Torque is produced in the rotor side. Any doubts? Any doubts?